All right, so this video is going to be pretty short and sweet, but it's going to play some pretty significant roles, especially when we start to get into buffers and titrations. Salts have acid-base properties. Some salts are going to be neutral, some are going to be acidic, and some are going to be basic. And it all comes down to what type of ions are making up the salt. If your ions are neutral, if they are coming from being paired typically with hydroxide in a strong base, or they are one of the anions making up a strong acid, then they are not going to have hardly any acid-base properties. And the example I gave you there is NaCl, but I could have given you NaNO3. I could have given you KCl. Again, any basically alkali metal, alkaline earth metal, and any of the anions that are part of your six strong acids, any combination of those is going to result in a neutral salt. When you have one of those alkaline metals or alkaline earth metals as your cation, but your anion is coming from a weak acid, the conjugate base of that, you're going to have some basic components because that fluoride ion in this particular example is capable of accepting protons. Whereas chlorine, if it accepts a proton, is going to turn into HCl and it's going to drop that proton right back off again. You need something that's going to be more willing to accept it. And the weaker substances are, again, because they are going to have more of an equilibrium state, are going to be more likely to do this. If your anion is from one of your strong acids conjugate bases, but the cation is not. The cation is coming from a weak base. Typically, those are going to come from ammonia. Ammonium would be one example, or some combination containing that NH as a cation. You're going to have an acidic salt. If you happen to really hit the jackpot and have cations and anions coming from both weak bases and weak acids, you have to compare their Ka values and their Kb values. If Ka wins out over Kb, it's going to be acidic. If Kb wins out over Ka, it's going to be basic. And if they're equivalent, then it will be neutral. If it happens to be a pretty heavily charged metal, transition metals like Fe3+ or copper, aluminum, if they are present, you are going to have an acidic salt because that cation is able to act as a Lewis acid. It's not a definition we had to get into, but it definitely expanded what can work as an acid. And these highly charged metals, and I don't see you running into them with anything other than a neutral anion, are very capable of acting as an acid and accepting electron pairs, which is what Lewis acids do. So when you're looking at these, you always want to make sure you pay attention to what type of ion the cations and anions are coming from. Are they coming from strong acids? Are they coming from weak acids? Are they coming from strong bases? Are they coming from weak bases? Remember, the cations are going to come from your bases because they're going to be paired with hydroxide. Or they're going to be paired with a weak base, but for salts, those are pretty much going to be hydroxides. And if your anion is going to be coming from an acid, a strong or weak acid. So in the case of calcium nitrate, we've got a group 2 metal, an alkaline earth metal, so that's going to be coming from a strong base. And then nitrate is paired normally with hydrogen as an acid to make nitric acid a strong acid. That would be an example of a neutral salt. If I look at my second example, I have sodium, which is an alkali metal, so that's going to be paired with hydroxide as a strong base. Nitrite, however, does not make a strong acid. It makes a weak acid. You can go find HNO2 on your Ka-Kb chart. So because nitrite has acid-base properties, this particular salt will be basic. HNO3, that's one of your six strong acids. There's really not any more debate that you have to do with this one. We know where this one's going to fall. With our next salt, ammonium nitrate, ammonium is coming from sorry, I'm not going to get this straight. Ammonium is not an alkaline metal. It's not an alkaline earth metal. So it is coming from a weak base. And then the nitrate is coming from a strong acid because that would make nitric acid. So this would be an example of an acidic salt, albeit a weakly acidic salt. Calcium hydroxide has hydroxide. The calcium part's fine, but the hydroxide part makes it be a strong base. So we know it's going to, we don't have to go any further with it. If you see that hydroxide, or if you have an acid that's one of your 6 strong acids, that tells you whether it's a strong acid or strong base. So if I was going to arrange these solutions, so these weren't all salts. The only ones that were true salts were the 2 on the left and the 2 on the right. But we were just asked to arrange these solutions, and it would be impossible to arrange the ones that are salts that weren't strong bases if we didn't understand what the cations and anions could contribute. Our most acidic would be the HNO3. Our next most acidic would be the ammonium nitrate. Then we have our neutral salt, calcium nitrate, our weak basic solution, sodium nitrite, and then calcium hydroxide. And so I think this is the last piece of this section. Here you do just have 4 full-fledged salts. We want to know, are these salts acidic, basic, or neutral? And if they're not neutral, what component of their salt allows them to be acidic or basic? So if we look at KCl, K is a potassium, it's an alkali metal, so that's coming from a strong base. Cl is coming, when paired with H, would make a strong acid. So this is neutral. We don't have to do anything more with this particular salt. With our next salt, we don't have an alkali metal or an alkaline earth as our cation, so that's coming from a weak base. The Cl is still coming from a strong acid, so this would be slightly acidic. And the equation that I would write would be showing how the methyl ammonium is able to donate a proton. Because we know it's acidic, with the cation always is going to have a positive charge. Chlorine was -1, so this had to be a +1 ion. In the presence of water, because these are solutions, that cation is able to donate a proton to water, producing a conjugate base, CH3NH2, which is decreased by 1 proton, and hydronium ions, which have increased by 1 proton. In my next example, ammonium fluoride. Ammonium is coming from a weak base. Fluoride is coming from a weak acid. We would need to compare the K values to determine whether they are acidic or basic. We see that the Ka for NH4+ is slightly larger than the Kb for F-, so this would be an acidic salt. NH4+ would be dropped into water. Again, notice that there's a double arrow. It's still in equilibrium because it is a weak acid. It's going to give up a proton to water, producing hydronium ions, and it's going to make ammonia. Kf, K is coming from an alkali metal, so that's a strong base that it would be making. F is coming from a weak acid, HF, so this is going to be a basic solution. And so it would be the F- combining with water. This time water gets to donate a proton. HF would be the conjugate acid of F-, and hydroxide ions would get formed. And it's because of what is made from those salts that allows them to be acidic or basic. You have hydrogen ions being made from the 2 acidic salts, and you have hydroxide ions being made from your basic salt.